ahead and start with the warm-up problem here. So I asked us to do two things: to find the magnitude, which is the same as finding the length of this vector, and then to normalize it. So for that first part where I'm looking for the length, oh, and I should point out that whether the vector is written like this or written like this, these notations are interchangeable for vectors. And once we get into 8.4, we're almost always going to be writing our vectors like this, not like this. Cool. Onward, we're finding the length. So to find the length of this vector, I'm taking each of the components and squaring them. So that'd be 2 squared, -1 squared, 10 squared. I'm adding those terms together and taking the square root. This is essentially us just sort of doing Pythagorean theorem in 3 dimensions, thinking about what's the distance from the origin to the coordinate to -1, 10. If I clean that up, that's 100 plus 1 plus 4. So the square root of 105. We talked about this a little bit on Monday, but normal when it comes to vectors means something else. But when we write normalize and we add that ending to it, it means that we're taking this vector A and we're dividing each term by the length or the magnitude. So that we're taking that vector A. Right now it has a length of, I didn't put that into a calculator, but it's a little bit more than 10. So right now it's got a length of a little bit more than 10. So if you think about, now I'm going to shrink that down by essentially chopping it and just taking one little piece. So to normalize the vector, I take each term and divide it by the square root of 105. Good times. That's it. That's all there is to normalizing the vector. By the way, we can also call this the direction of the vector A. So there are 2 different ways that we can conceive of direction. And when we're talking about vectors that only have 2 components, where we're really just talking about an X and a Y, we often give the direction as an angle. So we might give it as an angle in reference to the X axis. But when we talk about vectors that have 3 components, we typically give the direction of the vector as the normalized vector or the unit vector for that result. So when we normalize it, we can also say that this is the unit vector of A. And notation-wise, we can write that also as A divided by the magnitude of A. Can be computed, thinking about it as 2 vectors and multiplying components and adding between them. But it can also be computed by taking the magnitude of the vector A times the magnitude of the vector B times cosine of the angle between them. And oftentimes this side is super useful for us to compute things. And in particular, it's this side of the equation that's going to allow us to find that angle theta between 2 vectors. And the way we're going to do that is to rearrange this equation by dividing by the magnitudes for A and B. So I'd have my vector A dotted with my vector B divided by the magnitude of A, magnitude of B. That whole thing would be equal to cosine of the angle between them. Now, if you have vectors in 2 dimensions, you can go old school and fight through the geometry to find the angle between 2 vectors. But if we're in higher dimensions than just 2 dimensions, this is definitely the way we're going to find the angle between vectors. So let's do an example. I'm going to make my vector A the vector 2, -1, 0. And I'm going to make my vector B, let's go with 1, 3, 1. And I want to find the angle between A and B. Well, to find the angle between A and B, I'm going to have to compute a dot product and compute each of the magnitudes. So let's start with the dot product. So that top piece there for the dot product, when I take the dot product between A and B, mechanically, I multiply the two x values together. And I call them x values because I think about this as x direction, y direction, z direction. We could also just think of them as first component, second component, third component. So if I multiply those first components together, 2 times 1, I get 2. And I will add that to -1 times 3. So that's -3. And 0 times 1 is 0. In my denominator, I need the magnitude of A times the magnitude of B. So for my magnitude of A, I'll have 2 squared, -1 squared, and 0 squared, all under that square root. And my magnitude of B, 1 squared plus 3 squared plus another 1 squared. All in all, that means that on the top, I've got a -1, and in my denominator, keep me honest, make sure I get my arithmetic right here. That's 4 plus 1, so that's a square root of 5. And 2 plus 9, so that's square root of 11. Now at this point, all we know is that that's equal to cosine of theta. Unless this is some really nice number, like 0 or 1, this is the point where you reach for the calculator because we don't know what that angle is. Or if this is a test sort of situation, we would just leave it as theta is equal to cosine inverse of -1 over, and if you want, we can use a little algebra here to combine that as the square root of 55. Have a vector B and some other vector A, and I put them so that their tails are together, then the theta in this equation is living right here. One of the things that is used a whole lot in physics is actually these vector projections. And it comes up when we're talking about forces all the time. So what we mean when we talk about a vector projection is that I want to know if I draw a right triangle in here, how much of that vector B is in the direction of A? Or we can think about it as if I had a flashlight up here and I was shining my flashlight on the vector B, how long would the shadow be from that vector onto A? And we call this thing down here the projection. If I want to know the length of it, then we call it the scalar projection. And if I want to know what it is as an actual vector, then I call it the vector projection. For now, I'm just going to call it P. Well, if I call it P, then one of the things we can see from the geometry of the situation is if I know what that angle theta is, then cosine for this looks like the adjacent over the hypotenuse. So the length of P over the length of B. What that lets us do, if I come back over here to this equation, is I can actually swap out that cosine for the length of the projection divided by the length of B. So this would end up looking like A dotted with B over magnitude of A, magnitude of B is equal to, I'll swap it out for the length of P divided by the length of B. Well, now if I want the scalar projection, which secretly just means the length of P or the magnitude of P, I can multiply both sides by the magnitude of B. And this would simplify to look like the length of that projection is equal to A dotted with B divided by, and when I multiply both sides by the magnitude of B, it's going to cancel out on the left-hand side. So I'll just be dividing by the magnitude of A. And this one right here is the scalar projection. And our book gives us another notation for it. And the notation that our book gives for it is the comp. It's the comp of B onto A. That's how we read this. This means it's the scalar component of B projected onto A. Now I said that sometimes we want that as a scalar projection, meaning I just want to know how long it is. Sometimes we actually want it as a vector. And to turn this into a vector, we have to give it a direction because every direction has a magnitude and, every vector has a magnitude and a direction. So this portion is our magnitude and we stick in a direction by, and when we do this, we call this the projection of B onto A. This is the vector projection. And when we do this, we take that scalar component we just found. So A dotted with B divided by the length of A. And then we give it a direction by saying, well, if I look at this picture, we wanted the projection to be pointed in exactly the same direction as A. And if I want to know the direction of A, I multiply by the unit vector of A. That's what's going to give us that same direction. So I'm going to take my unit vector of A, which is A divided by its magnitude. This part right here is our direction. And it comes from the unit vector of A. You may have noticed there's a lot of vocabulary in chapter 8. There's a lot of vocabulary in chapter 8, but it's not too terrible. And although this looks really messy, it's not difficult to compute. Questions about this stuff? Because it is weird and probably uncomfortable. Yeah, sure. Let's do an example problem. I'm going to need a little bit of space on the board. Oh, sorry. It got a little blurry. This is the unit vector of A. Okay, so let's do an example. And I will try to insert vocabulary as we're doing that example. So I need a little bit of space. So I'm going to get rid of my picture. And these are really the two equations that we're going to work with. So I'm going to go ahead and get rid of these guys. I'll leave my dot product up there just because this is such a fundamental equation. Like this is kind of the heart of where everything's coming from. So here's my actual question part. So let's find the vector projection of B. And I'm going to start off by making this vector two-dimensional. Let's make this 2, 3. Vector projection of B onto A. And my vector A is going to be 5, 1. So because I've been asked to find the vector projection, I know I'm looking for this one. This is my vector projection. This part right here, we refer to as the scalar projection, or the length or the magnitude of the projection. This part right here is what makes it a vector projection, because this is the direction of the vector, or the unit vector for A. So let's get our pieces going. So I know in terms of the formula, I need A dotted with B. So let's start there. A dotted with B. And then here's really how I remember it. If I'm projecting B onto A, that means it should be sitting on top of A. There's lots of A's and B's in the formula. So I just remember that if I'm projecting onto A, then it should be sitting on top of A. So this part for our scalar component would look like, if I do A dotted with B, I'll have 5 times 2 plus 1 times 3. And that whole thing, I need to divide by the magnitude of A. Magnitude of A is going to be 5 squared plus 1 squared. So if I finish that off, 10 and 3, so that's 13. 5 squared is 25 plus 1, so square root of 26. We've got 13 over the square root of 26. That would be my scalar projection, or the scalar component of B onto A. Now, to answer the final question about the vector, I'm going to take this and say my projection of B onto A is equal to the scalar component we just found. Oops, drop in my pens. 13 divided by the square root of 26 times my unit vector of A. Since A is currently the vector 5, 1, to make it a unit vector or a direction, I would divide each component by the length of A. We can leave it like this or distribute the 13 over square root of 26 in. It actually doesn't matter. If we were doing this as a web work problem, the reason it matters is because web work would probably just give us 2 boxes to type into, which means we would have to distribute this in. So we'd have 13 times 5, 115, divided by, and when I distribute in the square root of 26 on the bottom, and I've already got a square root of 26 on the bottom, that'll just be over 26. And then my second component would be 1 times 13, so 13 over 26. And that would be my vector projection. 65. Oh, did I do math wrong? I did math wrong. 13 times 5. Thank you for helping me do math this morning. Cool. I'm ready to move on and talk about matrices. How about you all? A matrix is an array of numbers. So it's a way for us to organize big data sets. It's a way for us to organize lots of numbers and to do some cool math. But if I wrote 3, 1, 1, 0, 5, -7, this is a matrix. And this matrix has dimension to it, or size. This matrix has 3 rows and 2 columns. And if you've ever used an Excel sheet, you're used to matrices. You know how the columns are labeled, how the rows are labeled. And so if I wanted to grab the number 3 out of this matrix, that would be in row 1, column 2. If I wanted to grab the number 5 out of the matrix, that would be in row 3, column 1. Now, in general, in the English language, if you were to walk into a classroom and refer to the rows and columns of the chairs, it wouldn't really matter which direction you thought about them in. But the size of matrices has a lot to do with how we work with the algebra with matrices. So it is important that we have the same vocabulary. So for a matrix, these are the rows and these are the columns. Columns can hold up a house, rows get planted in a field. So I don't know if the last part helps, but the columns holding up the house helps me to think about these vertical things are holding up a house. So those are my columns. So this, the size of this matrix is 3 by 2. Someone told me long ago, just as a way to remember this, that all matrices are Roman Catholic. So rows come before columns. I've also heard RC Cola. Matrices drink RC Cola. Whatever's going to help you to keep your rows before the columns when we're talking about dimension. So I'm going to let this be the matrix A. By convention, when we talk about or label a vector, we use lowercase letters and a little vector symbol on top. When we talk about a matrix, by convention, we use capital letters. It's not like super hard and fast, but if you are looking at somebody's notes, especially if you're reading randomness on the internet and looking at somebody's notes, capital letters are almost always going to mean we're talking about a matrix, and lowercase letters are going to mean we're talking about a vector. So 3 by 2, and this is not multiplication. I read this as 3 by 2. This means that that matrix has 3 rows by 2 columns. So this is referred to as the size of the matrix or the dimensions of the matrix. Just like if we were talking about the dimensions of a room, we might say that a room is 10 feet by 12 feet, right? It's 10 by 12. Same kind of thing here. We're just saying that it's 3 rows by 2 columns. So let's see that my matrix A has a friend, B. And that friend B is 4, 1, 2, 3, 1, 1. Well, A and B have the same dimensions, which is good because I'm about to add them together. And if I want to add 2 matrices, in order to perform addition, they have to be exactly the same dimensions. And I think addition is the easiest thing to do with matrices because it kind of works just like you want it to. If I'm going to add these 2 matrices together, I'm going to get a matrix that's identical in size. So I will get another 3 by 2 matrix. And each component in that matrix I get by adding the pieces that are sitting in that spot. So this is going to have a total of 6 components because it is a 3 by 2 matrix. And to get what goes in each spot, I look at what's in that spot in the original 2 matrices. So to get what goes here, which is in row 2, column 1, I look at, well, what's in row 2, column 1 here, plus what's in row 2, column 1 here. So this would be 1 plus 2. This top spot, I'd be adding the 2 and the 4. Here, I'm in row 1, column 2. So I take row 1, column 2, plus row 1, column 2. here I'm in, and I'm just practicing the rows and columns vocabulary here. So I'm in row 2, column 2. So row 2, column 2 plus row 2, column 2. Row 3, column 1. Row 3, column 2. You do not need to write this step out. You can do arithmetic in your head. You are totally welcome to just write that down as 6, 4, 3, 3, 6, -6. I did it slowly because it's the first time we're adding matrices together. Now, you might ask, well, can you add just like a number to a matrix? Nah, you can't. If you're going to add matrices, we have to have two matrices that are identical in their dimensions. And when we add them together, we get a new matrix that has exactly the same dimensions. So if I wrote this out, what did I say? 6, 4, 3, 3, 6, -6. It is another 3 by 2 matrix. What if there's a constant? So I said that we can't add a constant to a matrix, but we can multiply a constant. So if I wanted to find -3b, that means take every number in b and multiply it by -3. So I'd have -12, -3, -6, -9, -3, -3. Kind of boring. The interesting stuff happens when we try to multiply a matrix by another matrix. Yeah, so there's a question about, is the process the same if we're adding multiples of matrices together as if we were adding multiples of vectors together? Completely the same. So if that's -3a, and I asked us to compute, or sorry, that's -3b. If I asked you to compute 2a minus 3b, well, since we already computed the -3b part, we just have to compute the 2a. So I would take twice that matrix A, 4, 6, 2, 0, 10, -14, and add that to our -3b matrix that we just found, -12, -3, -6, -9, -3, -3, and get, testing my arithmetic, this is a bad idea, keep me honest, 4 plus -12, that's -8, 6 plus -3, I'm going fast, 2 plus -6, -4, 0 plus -9, -9, 10 plus -3 is 7, -14 plus -3 is -17. Well, if I want to multiply these two matrices, the first thing that I need to know is what the dimensions of the two matrices are. So my matrix M here is a 2 by 2 matrix. And what's the dimension of P? You can type it in the chat. While I sneak a sip of coffee. That's right, matrices like RC Cola. Therefore, I've got rows, the 4 columns. So this is a 3 by 2 matrix. Well, I know the rules. You probably don't know the rules yet unless you somehow made sense of section 8.4 on your own. The only order that I can multiply these two matrices in is P times M. So if I wanted to multiply P times M, the dimensions of P are 3 by 2. The dimensions of M are 2 by 2. And the way that I know that I can do this multiplication is that when I stack them up like that, these inside dimensions are the same. And then these outside dimensions tell me the size of the final result. So I'm about to multiply P times M, and that's going to give me a matrix that is 3 by 2. I kind of wish I had written them in the opposite order so I didn't have to write all this again, but it's okay. We got this. Here's my matrix P. 1, 4, -1, 2, 3, 5. And I am multiplying that. And just for a reminder, that's a 3 by 2. And I'm going to multiply that by 2, 1, 0, -3, which is a 2 by 2, which means my final result, and I'm giving myself lots of space because I'm going to have lots of arithmetic in here. But my final result is going to be a 3 by 2. Now, I know I made it really big, but I made it big because I am going to have, since it's a 3 by 2, I am just giving myself the space to do my arithmetic. I'm going to do this first one slowly, and to help sort of show the process of what we're doing. So the first thing that I do is I get the 6 pieces that I know I have to fill in, and then I label their coordinates. So this is in row 1, column 1. That is in row 1, column 2. This is row 2, column 1, row 2, column 2, and finally row 3, column 1, and row 3, column 2. And the reason that I label them, at least when you're first getting started with matrix multiplication, is it helps to remind me what arithmetic I'm actually going to be doing. Row 3, column 2. So for example, to get the number that goes in this spot of my final matrix, I'm going to take row 1 from the first matrix and multiply that by column 1 of the second matrix. So to get what goes here, I'm taking row 1 times column 1. And when I say times, technically it's a dot product. I'm taking the components that are sitting, first components multiplied together, added to second components multiplied together. So what goes in this spot looks like 1 times 2 plus 4 times 0. Then I would move on. This next spot says I'm taking row 1 times column 2. So the same row 1 from matrix 1, but this time I'm multiplying by column 2 from matrix 2. So now I'm moving over here. So what would go here looks like 1 times 1 plus 4 times -3. And I promise you'll get faster at it after you do 40 of these. But taking your time at the beginning does, at least for me, really helps. So is that 1, -3, 1, -3. And I'm going to stop circling things so I don't have to keep erasing them. But what goes here should be row 2 from the first matrix times column 1 of the second matrix. So I'm focusing on row 2 and now times column 1. I'm going to just do the arithmetic. So -1 times 2 plus 2 times 0. Here I've got row 2 times column 2. So row 2 of the first matrix times column 2 of the second matrix. I've got -1 plus -6. Row 3, column 1. Row 3 of the first matrix times column 1 of the second matrix. 3 times 2 plus 5 times 0. Last but not least, row 3 times column 2. Row 3, column 2. 3 times 1 plus 5 times -3. So 3 times 1 is 3 plus -15. And again, once you've done a bunch of these, you can do all of that arithmetic in your head. And you would not have to show work for this. You could just jump straight to a final answer that looked like 2, -2, 6, -11, -7, -12. So when the inner dimensions match, so that means that we can do the multiplication, and then the outside dimensions from what we multiplied together tell me how big the final result is.
Okay, thank you.
Yeah. So if I just had, like if I were multiplying a 3 by 4 times a 4 by 1, then my inside dimensions match. So we're allowed to do that multiplication. And the final answer would be a 3 by 1 matrix.